Okay, 1 minute. Okay, recording products. So I think we can start our session. And Ivan, what happens with the screen? Okay, Bart can help us. Okay, thank you, Bart. Okay, let us start our seminar today. Our speaker, Volodya Rubtsov from Angers University, I think, and some second ITP run. So he will talk about Kontsevich and Buchstaber polynomials, multiplication kernels, and Gaiur D differential operators. We can start. Okay.
Okay. First of all, thank you very, very much for this invitation. It is always a pleasure to speak in this audience. And traditionally, I'm usually starting with some excuses. Today, my excuses are because of my voice and because of my health. I'm not very healthy, unfortunately, but hopefully I'm in Zoom, so you are safe and my viruses will not touch you. Of course, if they are not virtual. And the second, I want to warn that probably, very probably, I will not succeed to tell all this huge story. The story which I will tell you, in principle, should be. I had two experiences with 2 hours talk in Rio and in Steklov Institute. And almost even in 2 hours, it was difficult to finish completely the story. So I hope today to start and to stop at some point when the time is over. And if you are interested, and I can continue it at any other moment which will convenient to you. The story is so beautiful, so I decided not to reduce it to a part of it, because it is just like to show only one part of an elephant to some blind person. That just if you show only one part and he touches this part, he has a wrong impression about the whole elephant. So I want to try to show the whole elephant, and at least not to show, at least to touch all parts of this elephant. The story is a part of 2 papers in progress with Ilya Gaiur and Duke van Straten and Victor Buchstaber, and also with Ilya from Toronto University, Duke van Straten from Mainz, University of Mainz in Germany, and Victor Matveevich Buchstaber, as you know, in Moscow Steklov Institute. So let's go ahead. The main object of my... Do you hear me? Vanya, Andrei?
Yes.
So
we can.
I ask you, please, you can stop me and ask any questions at any moment.
Okay.
So the main object of my interest and of this study is so-called multiplication kernels. What does it mean? If you see this formula, you can just imagine some very vague situation. For simplicity, you can imagine that you have a eigenvalue problem for some differential operator, and you have eigenfunctions big psi with eigenvalue lambda. So we take we have one function in 2 different points with the same value of lambda, and take the product. And if we are able to express it in integral form as an integral over some cycle gamma, from the value of the same function with the same eigenvalue in the point z, integrated over z with some so-called integral kernel, which depends on three variables, x, y, and z, integration variables. And this kernel, in principle, doesn't depend, it is important, doesn't depend on lambda. If we succeed to find such a representation, we will speak that we have a multiplication kernel. The situation is classical and quite well known. I will show you many interesting examples, historical and modern, of such structure. But I want to say in advance that you can guess very, very vaguely also that this formula looks like a product in some associative commutative algebra with structure constant playing the role this kernel function k. So it is some idea which goes back to Maxim Kontsevich. The second
the contour is also lambda independent.
Well, I don't want to precise it. It normally it depends on the measure. What you, for example, it might be just a residual formula. It's typical example of residual formula with this. But it is dependence on lambda only in these functions. Hello, Harry.
Thank you, Volodya.
The second subject. The second subject is also absolutely beautiful and well known. It is so-called quantum differential operator of P to n minus 1, and or in I will call it very also very vaguely n Bessel operator. In fact, it is not n Bessel. It is my nickname for this, but in fact it is operator for n equal to 2, which is close to Bessel operator, and I will discuss it for n equal to 2 in more details later. This operator is well known in mirror symmetry and Dubrovin-Frobenius manifold theory very well. And it was the story about this operator, our main result with Duca and Ilya, that we, in some sense, handled some kernels related to this n-Bessel operator in the same way like people handle solutions of so-called Calabi-Yau differential operators, though this operator is not Calabi-Yau, but we are able to find some Picard-Fuchs equation for kernel of this operator, and combinatorics, interesting combinatorics related to this is one of our main results. And the last but not the least, it's two families of polynomials which are beautifully appeared in this story. One, so-called Buchstaber polynomials. It is a family of polynomials with three variables x, y, z, and three parameters, which at the moment I suppose just complex parameters. I wrote this for sake of briefness. I wrote it in terms of symmetric, elementary symmetric function, because these polynomials, they are beautifully symmetric in x, y, z, so they can be expressed in terms of sigma 1, sigma 2, sigma 3, standard symmetric elementary polynomials. And it has very nice form. Of course, everybody immediately understands that this form is a kind of discriminant of some quadratic polynomial. And these polynomials were introduced by Buchstaber in 1990 in his paper when he studied some elliptic laws of very special formal groups related to another formal groups. And he described this polynomial like a family who govern all these two formal elliptic group of so-called square module type. If I have time today or another opportunity, I will discuss it in more detail a little bit later. And the last, it is so-called generalized Kontsevich polynomials. This is also polynomials in three variables x, y, z with three parameters a, b, c. And it is also can be written as a discriminant of some quadratic trinom. And I wrote it also here, delta sub t, it means discriminant of this trinom with respect to t. And sigma 1, sigma 2, sigma 3 is the usual elementary polynomials. You see that this polynomial looks a little bit different than Buchstaber family of polynomials. But once I just discovered that for some special value of parameters, these two families of polynomials give the same zero locus. And it was a trigger of my interest how they relate in general. And is it possible to establish some formal group law related to generalized Kontsevich polynomial as well? And of course, we discovered that it is possible. And moreover, this is very well known group law. It is so-called two-cassette construction of Buchstaber and Elmer-Ries. So that's what the area what I want to show you today. The connection between all this object, very, very approximative in this complicated simplex. So here, these two-valued groups, which are one of common point for all these objects. Here you see this Kontsevich polynomial, Buchstaber polynomials, and also I didn't say interesting observation, which also can be easily discovered, and probably Harry can guess easily what this observation means. This observation that both families of polynomials are so-called discriminantly splitted. It means that if we take these polynomials, they are symmetric, as I told you, in x, y, and z, and also they are quadratic if we write these polynomials as a quadratic function of any of these three variables. Then we can compute secondary discriminant of these polynomials with respect to any of variables. And this secondary discriminant becomes splitted. It means it is factorized in very, very simple form as a product of two cubic polynomials, the same cubic polynomials of two other variables. For example, if we compute discriminant over z, then this secondary discriminant split it as a product of some cubic in x and the same cubic in y. Such polynomials, they are called discriminantly splitted. They were described by Volodya Dragovich, a former student of Boris, in his works in early of this century, 2009, 2010. And it was observation that such property to be discriminantly splitted is intimately connected from one hand side with two-valued group laws, and from other hand side from interesting family of integrable systems which generalize so-called Kovalevsky top. But there is also one interesting and very important connecting point for all this notion. It is so-called Descartes theory of generalized shift operators. This theory is a classical subject of analysis. Formally, they were introduced by French mathematician Delsart in 30s and developed in the works of Levitan in 50s, and big progress was in understanding this notion and relation this notion with representation theory was in the papers of Gelfand and his school, Graev, Vilenkin, and the beautiful paper Gelfand and Felix Berezin. And these operators are interpreted from the viewpoint of representation theory, like some differential operators on homogeneous, on symmetric, special type of symmetric spaces, so-called Gelfand pairs, and the corresponding integral formulas, which I will show you. It is just a product of some spherical functions related to these operators, and it is a subject of well-known and very well studied in 50s and 60s. So, but the roots of my story goes even very far in the 19th century. So it is a famous in number theory and in classical analysis. It's a very famous so-called Clausen duplication formula, which relates a square of hypergeometric Gauss and generalized hypergeometric function f subs 3,2. And the parameters of these two functions are as I show. This Clausen duplication formula is very well known object, and it is a partial case of the phenomena which I call the multiplication kernels. So why it is so? It is easily understandable from the next historical example of such. So duplication formula, it means that I take the function in the same variables, but in principle, British mathematician Bailey, he studied beautifully products of hypergeometric and generalized hypergeometric functions with different variables, such that the Clausen duplication, it is just a partial case of the Bailey results. And there is a monography where all these formulas, of course it is, most of these formulas are in Bateman-Erde monography, very famous. So the next, I'm sorry, the next story is this analog of my product for degeneration of hypergeometric functions, so-called confluent hypergeometry. These functions into different points, and x over 2 and y over 2, can be written as an integral of the same function, but the argument of this function now, it is a kind of scalar product. And this is, you see this, x and y, it is a square length of vectors x and y in a Euclidean space R to n. This integral is integral over n minus 1 dimensional sphere. This is invariant measure on the sphere. And this typically formula from representation theory of so-called Gelfand pair related to elementary symmetric space R to n. C of R to n, it is an algebra of functions on this symmetric space, invariant with respect to n-dimensional orthogonal group. And this product can be algebraically interpreted like a product like a co-product in this commutative homogeneous coalgebra when you interpret these invariant functions in terms of formal series. But of course, without this interpretation in geometry, in pure confluent hypergeometric terms, this formula was obtained the first time in paper of Schlafly, Basel mathematicians from Swiss in 18th century. And it is interesting that only for n equal to 2, for this parameter n, when this confluent hypergeometry easily can be reduced to Bessel, we have so-called example of two-valued cyclic formal group. Now, about Bessel. Of course, independently, people do the same, and they didn't care about it, and they didn't know about it. In this, more or less, in the same time, Russian mathematician Sonine and Austrian mathematician Gegenbauer, they proved beautiful formula for products of zero-kind Bessel function in terms of this integral form with algebraic kernel. Yeah.
Okay, thank you very much.
I don't hear. Can you? Sorry, Sergio, can you repeat, please?
I think we can continue.
Okay. So this is also very important and very inspiring for us formula. I will come back to this formula from the point of view, the second object of my interest from this n Bessel for n equal to 2, and I will explain why this algebraic kernel 1 over square root of this quartic function is indeed example of my family of invariant polynomials Kontsevich type. So of course, these Kontsevich polynomials, they are not here for nothing. There is a class of so-called problems for D2 differential operators, which also people in number theory called small a priori operators. These operators looks as follows. Let's take any cubic of this form, and then consider the eigenvalue problem for operator where this cubic put between two partial derivatives over independent variable t. And then the solution of this eigen problem, small phi with eigenvalue lambda, written in this product form, gives you also example of multiplication kernel, and this multiplication kernel is exactly this Kontsevich type discriminant polynomial, because if you take the difference between cubic f of t and the product of factorization with the roots x, y, z cubic, then higher terms t cube will disappear, and you will have only t square in this polynomial. You can easily compute the discriminant, and you obtain function p. And this function p, of course, will also it is an example of beautiful algebraic kernel. So now, why Kontsevich was interested in such strange operator? Kontsevich wanted to make explicit so-called Lenglen's correspondence for SL2 local systems on projective line over finite field with prime characteristic P different of 2. So the local system on this line minus 4 points, usually these points are 0, 1, t, and infinity. We suppose that the monodromies around these points, they are unipotent local monodromies. Then he conjectured that if we consider the corresponding Hoyne equation, which is similar to what I showed you for small a priori case, but now it is for any cubic with coefficients a, b, and c, and this construction, you see, it's similar construction. Then we have Hoyne, special Hoyne equation, and the question which Kontsevich wanted to study, how to express Hecke operators acting on analog of cusp forms for this case in terms of this given local system data. The same question was studied in master thesis of Drinfeld student Tiruji Thomas, and later in the thesis of Niels Wied de Bos, student of Heinloch in Essen University, and also he was a postdoc with Duco and Straten. And the idea of Kontsevich is the following. If we take the finite field with prime characteristic different from 2, then for any point on the projective line, we can define such operator given in by p plus 1 times p plus 1 matrix with entries from this field. And the matrix entries in the which indexed by y and z in the point for operator hx are computed in the following. It is 2 plus cardinality of sorry, I just always forget to correct this small misprint. It is a small misprint. Here it is w square. It's a number of w which are w lying on this curve. W square equal p of x, y, z plus some correction terms maybe. It is very, very in fact, I want to say that even in Kontsevich paper, original paper, the formula is not completely correct, because the expression which he wrote needs some correction to have this miracle which he announced, namely such operators, they commute if you compute them in 2 different points x and y. So this commuting family generates a commutative algebra, which people usually call Hecke algebra, and this algebra acts on the function over this line, and acting this function can be represented in vector form with vector coordinates v sub x, and then action this operator, Hecke operator on such vector function in the point y gives by this a very, very simple form. And so Drinfeld in his paper said that when we have atomorphic PGL2 representations of a function field Phi of t, then these representations are correspond to normalized Hecke common eigenvectors, because they are commute, they have a common set of eigenvectors, and they correspond by this correspondence to automorphic representation of PGLF. Well, it is not exactly, we should speak about, well, I want to just to skip these details because we should speak about Adel, and I don't want to go further. My interest was if it is possible to consider for the case of C, and this beautifully was done in series of papers of Ettinghoff, Frenkel, and Kashdan between 2019 and 2023. The last paper was published in archive very, very recently. They wrote 3 or 4 papers. And this is completely analogical approach, namely instead of the curve P1 over finite field with this product multiplication product formula via operators, they proved that for P1 of C minus 4 point, one can define really Hecke operators which acts in some Hilbert L2 space of half densities, and these Hecke operators can be written in multiplication form like an integral operator with the kernel, and this kernel is exactly generalized Kontsevich polynomial, which I showed you from the very beginning. This is a absolutely beautiful result. It was also motivation of our study of such family of polynomials. Now, maybe I go to explanation one of these vertices of my correspondence, namely, sorry, I see this, Andrei, I see a question. Can I read it or you read it?
Okay. Any comments? Any questions?
It is just written in the chat that Sergio didn't mute himself.
I see. So I remind what is I understand under two-valued group. It means that we have for any set X, we have some operation which we call two-valued multiplication law, which is mapping from Cartesian product of X cross X to symmetric square of this set. And this multiplication law also enabled with so-called unit element E from this set and inverse element X2 minus 1, such the following 3 axioms are satisfied. First, associativity. It means that if we have 3 elements of our set X, then we have a coincidence of 2 4-element sets. If we take this 2-element set X cross X star Y, and then we have star with Z in this order, it is the same element with 4-element set that X star with Y star Z in this order. So the second axiom, existence of so-called strong unity, it means that for all X from this set, it's a misprint, for all X we have E, our unit left and right, gives the same two set element in symmetrics XX. So third one, it's existence of inverse. It means that for each element X, we have two sets X star, X to minus 1 from right and X to from left and from right, and then they contain the inverse. They contain the unit element E. I want to say that existence of inverse, I want to stress, in principle doesn't expect unicity of it. But for many concrete examples, one can prove that such inverse is unique. My main example and relation to this polynomial is very, very beautiful, and it's a toy model, if you want, of many other relations with two groups and n groups. It is the following: if we consider complex numbers just with addition operation, and this order 2 automorphism, evident automorphism Z, which goes to plus minus Z, then we have two-value group structure on the quotient C over Z2. Namely, multiplication law for this two group is given by this very from the first glance, maybe not evident formula. But this formula becomes evident if you consider the following map. You consider representation via symmetric elementary symmetric polynomials in Z1, Z2, and the map from C2 to C2, which just expressed Z1, Z2 as sigma 1, sigma 2. And then we have the following polynomial. Let's consider polynomial quadratic in Z with second term as a coefficient. We take minus 2 times x plus y, and the free term x minus y squared. Then this polynomial we can rewrite in the following discriminant form. So it is a square of linear z plus x plus y minus 4 in this elementary polynomial sigma 2. So we express it in terms of sigma 1, sigma 2. Discriminant of this polynomial, of course, gives you multiplication by two roots of this quadratic polynomial. We have these two roots. If we solve this equation, we obtain exactly the operation between x and y, or it is the same between x to minus 1, y to minus 1, given by the formula which I start. This observation was known to since I would say 70s, when Buchstaber and Novikov started to study the two-valued group laws, but in such refined form, it appeared in the paper of Buchstaber and Ries. Well, it is just a reminder to two-valued group. Now, what I go further, I need to remind a little bit about Calabi-Yau differential operators and how they comes from mirror symmetry. And then I will try to relate the following things: the Calabi-Yau differential operators. Then from Calabi-Yau, I will go to quantum operator of n Bessel type. I probably will succeed, but I'm not sure, to explain non-abelian Abel theorem in this context. It was just a small interpretation of multiplication formula for our for our context, and also how it relates to Buchstaber and Kontsevich polynomials, how they relate between them, how Buchstaber and Kontsevich polynomials can be written one via another. This is also a very interesting story, which we described with Ilya and Victor Buchstaber recently. And of course, I will have no time to discuss many interesting things, maybe in another time, especially my personal interest, how these multiplication formulas are related to the question of separation of variables and the problems with multiple accessory parameters, and how multiplication formulas are related to so-called quantum rational Bavil-Mukai systems, which we introduced with Benjamin Enriquez in our paper in Duke in 2002. It's an absolutely separate story. Okay, and also I want to give some references if people want to read something about it. The best source of information about Bessel functions and Bessel function identities, of course, the classical course of Watson, and relation with the Gelfand schoolwork, and it is a beautiful paper of Naum Yakovlevich Vilenkin, Special Functions and Theory of Group Representations of 1964, translation almost immediate in English. Then this series of papers of Ettinghoff, Frenkel, and Kazhdan, for example, paper Hecke operators and analytic Lagrange correspondence for curves over local fields. Philosophically, the ideology of this multiplication formulas and non-abelian-abel theorem, it's in our paper with Vasily Goloshev, Anton Melit, and Novikov and Straten. It is, for some reasons, it is not still published, because this paper, it is very just a preprint form of some ideas, and then these ideas are realized by different people in different combinations. Very good and full introduction of multiplication kernels technique, and many examples, very technical, very well computed by Maxim Kontsevich and Sasha Adesky in their paper 2021, where this philosophy of multiplication kernels also interpreted in different form. So, and our papers are not yet put in archive, but I hope this year we will finish before New Year both. Okay. So plan of my talk, I just briefly said about it. I will remind about mirror symmetry and differential operators of Calabi-Yau type. Then I will go to Bessel. It's my central point. And I hope to share with you with some so-called experimental mathematics, because many results which we obtain, they are experimental character results. It is just some computations and discoveries after these computations. Some of them we were able to prove, some of them are still just miraculously conjectured. So I will start with this reminder. First of all, what is the Calabi-Yau differential operators? Probably you know what it is, but I need to say a few words anyway. So under Calabi-Yau differential operator, I will understand Monique differential operator of this type. Here, theta, it's a logarithmic derivative. It's d over dt, which people very often in this area used this representation. The coefficients of these operators in degrees t in some degree are polynomials of theta of the same degree. So it means P1 it's theta degree 1, P2 it's this polynomial degree 2 in theta, and etc. And we suppose that the origin is a so-called maximally unipotent monodromy point, it's a MUM point. What it means, I will explain just in the next slide. But I want to say that such operators, they, if you never had idea where they came, you can easily find such type of operators if you consider the Gauss-Manin theory, Gauss-Manin connection theory for periods, for some families of Calabi-Yau varieties. And such periods, they satisfy so-called Picard-Fuchs differential equations. If we write the corresponding differential operators, they will exactly this type. What the property to have maximal unipotent monodromy, it's very nice property, in fact. I will often use this property in future for good reasons. The reason that monodromy matrix, if the point is MUM, can be by conjugation written in the one Jordan block triangular form with such structure. And the advantage of this form is that we can write the corresponding fundamental solution for this differential equation with this operator in the vicinity of this MUM point. In this form, like a combination of degrees of logarithms, and first phi sub 0, it is a holomorphic analytic solution, and other solutions in the fundamental system, they contain some degrees of logarithm. And such operators probably you know very well for small dimensional Calabi-Yau examples. For elliptic curve in Legendrian form, you have very famous Picard-Fuchs equation for this period, for this differential dx over y. For n equal to 2, Calabi-Yau will be K3 surface. So we have different description of K3 surface. For example, in P3, it is a so-called quartic family of Dwork type. This Dwork type will often appear in my talk today, probably. The corresponding Picard-Fuchs equation is the following. It's T23, it's a cubic, and for n equal to 3, the most interesting for mirror symmetry Calabi-Yau threefold with the Hodge number H21 equal to 1. We have Picard-Fuchs order 4 for this Dwork quintic in P4, and this typically you see the structure of these operators is very similar. Now, how it relates to so-called mirror symmetry and corresponding enumerative problematic. It was started probably again, you know better than me that it was started in early 90s in the paper of physicist Philippe Candelas, Xenia de la Osa, Green, and Linda Parks. and they consider this exactly this order 4 Calabi-Yau differential operator, which correspond to this quintic. And then let's consider the structure of solutions of these fundamental solutions in the vicinity of t equal to 0. Analytic solution, it's a fantastically beautiful hypergeometric form with integer coefficients. And the next solution, phi sub 1, which is a combination with logarithm of initial analytic solution coefficient, but the second term, phi f1, it is no more integral. It means that the coefficients of these solutions are rational but not integer. This was cured by Yao and Lian in '96, and the idea was to introduce new coordinate q of t, which is exponential of ratio phi sub 1 over phi 0. So this function q of t can be written in series again with integer coefficients. This series starts with t. It means that we can write integer coefficient series starting with t, and we can invert it and express t in terms of q as a function of q. So this, what people call mirror map, and the corresponding q is called canonical coordinate in this context. So the inverse series t of q, no more integer, of course, it starts with q plus q square over series times series with rational coefficients, and the solutions of my equation in terms of coordinate q can be rewritten, of course, can be rewritten. And when they rewritten, then we obtain again a miracle, and this miracle that if you take the so-called Yukawa coupling or Yukawa potential, then second logarithmic derivative in q of phi 2 over phi 0 is again fantastically integer coefficient series. But
Volodya,
да.
This is Maxim Pavlov. Could you please say just few words about convergence or divergence of these series?
No. Just I'm speaking just about formal series here.
Mm-hmm. Okay.
Then we can go further. Instead of considering this series in Q, we can rewrite it as a so-called Lambert series form, and then reload it in not in Q but in Q to some degree k over 1 minus qk. So instead of Q, we will take this Lambert series representation. Then we again have some set of integer numbers, and these integer numbers n sub k, we have a common factor 1 over 5 times q k to 3, and these integer coefficients, they are fantastically famous. It is so-called instanton numbers, and they are related to Gromov-Witten invariants, which are in enumerative geometry enumerates number of degree k rational curves which lies on generic degree 5 threefold in P4. And people in algebraic geometry, they knew only first two numbers. It was a classical result of enumerative geometry of 19th century for lines, it was by Schubert in 1886, and for conics, Sheldon Katz 100 years later in 1986. And then a physicist proposed the third one, and confirmation that physicist computational conjecture is again gives some enumerative invariant was checked mathematically by Ehrenzuth and Ströme in 1993. But the most impressive result was, of course, Lian Liu, Yao, and Giventhal result that all these instanton numbers, they are exactly Gromov-Witten invariant. So this is an issue of this mirror symmetry theorem. We want to announce that we have an analog of these instanton numbers for non-Calabi-Yau differential operators, but for this n Bessel operators. But we don't know enumerative sense of these numbers, and this is an open question which I address to everybody. If you can, maybe they have also some Gromov-Witten type invariant interpretation, maybe not, I don't know, but it is interesting that we also have some set of integer numbers which looks like instanton quasi-Calabi-Yau. Okay, because of lack of time, I will not go into formal definition of Calabi-Yau differential operators. Now people know many of them. I showed you three first Calabi-Yau operators, and for example, for n equal to 4, I just want to say that all singularities should be regular. The origin should be mum point, maximally unipotent.
Lodya, maybe you can stop here and continue after 2 weeks, maybe.
Okay, if I should stop. Okay.
Yes. We
After
touch very nice elephant.
okay. If you agree,
Huge elephant.
for me it is better because it means that I can speak calmly without jumping.
Okay. So in December 12, yes. Continue your talk.
Okay, December 12th.
Any questions? Any comments? Very nice talk. Very interesting. And we can see that it is a really.
I still didn't start, in fact.
Yes. Only one small part of
Just only one
of your elephant. I will not say which part, but okay. That nice. Thank you very much, Volodya. I will want the slides of this part.
I'll send you.
Yes. Thank you. So, any comments, questions by Zoom?
I'm sorry for my, like we say in French, état grippal.
No, it was very nice voice. So I hope that after 2 weeks you
I hope.
will health, and we continue our discussion. Thank you very much.